Now listen up, here's a story about a bunch of guys who discovered atoms. Actually, the situation's a lot more nuanced than that, as we're going to talk about on this page. And also, you may notice that there's only 4 men on this part of the curriculum because women just get written out of the history entirely. But women aren't on the state curriculum. So, okay. Let's talk about atomic theory. I'm going to be underlining key words as we talk about this, and I encourage you to do the same. These keywords are going to be the things that you should study. So here we go. Let's talk first about John Dalton. He was working on the first modern theory of atoms. He published his theory in 1803. And for a long time, decades, people were like, that's not real, right? That's not a thing. This dude's an idiot. But then it turned out, actually, he was not an idiot. So, you know, that's just how things go. He had some postulates in his atomic theory that basically a postulate's like a theory. That's a word you should learn in geometry class. So I'm not really gonna go over it in too much detail, but he had some postulates, and we've boiled it down to 4 points here. All matter is made up of extremely small, solid, indivisible particles, which he named atoms, from the Greek word atomos, which means indivisible. Atoms of the same element are identical, and atoms of different elements look different. Atoms are neither created nor destroyed. They can only be rearranged in chemical reactions. And compounds consist of atoms of elements combined in simple whole number ratios. That's compounds specifically that we're talking about there. Now, some of these things ended up not being true, but there was no way for Dalton to know that because the technology did not exist to disprove some of these postulates. And some of these postulates, you can see, we still believe to be true based on our current understanding of the universe, which again is largely based on the technology available to us. I guess it's possible that one day number 3 and 4 on this list could be disproven by some new discovery in technology, but at the moment, it's not looking super likely. Let's talk about what's not true about number 1 and number 2, though. In number 1, that word indivisible is not true. It turns out you can divide atoms. There are lots of ways you can divide atoms, but the most obvious ways are into protons, neutrons, and electrons. You can divide atoms into protons, neutrons, and electrons. Like I mean, they exist. But the thing is when Dalton was working, he didn't know, no one knew they existed. And that we would not have the technology to discover those things until over 90 years later. So he had no way of knowing that you could subdivide atoms into those things. It was literally not possible to understand at that time. And then in number 2, atoms are of the same element are identical. Different elements look different. The false word there is the word identical, because it turns out you can have 2 atoms of the same element that are not the exact same as each other. That is called isotopes. And we will talk more about that later in the unit. Welcome to Unit 2, by the way. I didn't actually present this in any form when I started this video, because for me, again, the same shirt, same day. But for you, time has passed. Yeah, welcome to Unit 2. Enjoy. Okay, so yeah, Dalton had these 4 postulates. You'll need to know what they are. Those keywords that I underlined are the key to making sure that you are able to recognize those 4 postulates, and definitely know which ones were not true and why. All important toward this unit. Next, we got to talk about J.J. Thomson, who was working in, well, also before, but he published his stuff in 1897. So like I said, now 94 years have passed between when Dalton published his paper on atomic theory and when J.J. Thomson gets credit for discovering the electron. I say gets credit for discovering the electron because he was not the only person to do it. He was just the one who did it the most famously. And this is sort of a problem in math and science in general, is that like there were actually lots of people who end up discovering the same thing around the same time as each other as technology becomes available for them to do it. And then usually a white dude gets credit. That's like just how it happens. But like there's actually a lot of historical accounts that J.J. Thomson was kind of a jerk and like stole research from people and stuff like that. But it's, you know, fine. We can just keep giving him credit for discovering the electron. Anyway, J.J. Thomson was doing some experiments with something called a cathode ray tube. That's this thing over here. It was a glass tube that they vacuumed the air out of. They put some electronic, or I should say some metal plates in there, and then they beamed electricity through it. And as the electricity went through, you could actually see it looked like light coming through, like it looked like a laser beam kind of. But the thing is that it reacted to magnets. Like this little beam of light would be coming through, and then you could put a magnet next to it and it would make the beam like bend one way or another, depending on which way, like which type of magnet you put next to it. I will probably put up some like videos you can look at of what a cathode ray tube looks like, just because it's interesting to like watch. I'll link them on Schoology or something, assuming that's a thing you can do. Again, this is for past me who is recording this. It's July and I don't have access to Schoology yet, so I don't really know if I can do that, but I'll find a way. I'll put some videos where you can watch of what a cathode ray tube looks like just on YouTube, because it is like really interesting to just look at. It's wild. But anyway, when he saw that they reacted to magnets, he realized that this beam of light can't actually be light, because light does not respond like matter, right? Like if I held up a little laser pointer and put a magnet around that, the light beam from the laser pointer is not going to bend. That's not how light works. So because the beam was bending in the presence of a magnet, that told him that this must not be light, it must be matter. And so he did some more experiments and discovered atoms can be subdivided. His experiments with cathode rays helped him discover that atoms actually contain small negatively charged particles called electrons. So J.J. Thomson gets credit for discovering the electron, and he did that using cathode ray tubes and other people's research. He also published something called the Plum Pudding model, which was basically what his new idea of what an atom looked like was. Before, during during Dalton's time, we pretty much just thought of atoms as being like a sphere, just a solid sphere, just like a ball. And after Thomson discovered that electrons exist, he was like, well, obviously there's other parts to an atom, and these other parts are electrons. And so what he thought was that an atom must look like plum pudding, where there's like electrons floating around in the atom, just kind of loosely chilling there in the middle of a bunch of basically like positive charged stuff. I don't think he had a good like theory for what that positively charged stuff was. He just was like, yeah, the electrons are floating around in there. That's just what they're doing. That's just what they're doing. Again, he didn't super have a good like explanation as far as I've ever found of what the positive stuff was. He didn't really need to because someone disproved his theory not that much later. But anyway, I do want to show you why this is called the plum pudding model specifically. And that's because British people, J.J. Thomson was British people don't think of pudding the way that Americans think of pudding. Like when you think of pudding, you probably think of like a snack pack, right? Like those little like tubs of like pudding and you just eat it with a spoon for lunch, right? That's probably what you think of as pudding. But British people would call that custard. And when they talk about pudding, they're actually talking about something that's more of like a wet cake, like this. This is literally plum pudding. It's traditionally like a British Christmas dessert. And you can kind of see there's like pieces of plums just floating around in there. And then there's this like gooey bread stuff. And he thought the electrons in an atom were like these little pieces of plum floating around. And he thought the gooey bread stuff was basically just whatever the positive stuff in the atom must be that kept the negative electrons there. That was the best he could come up with. Maybe because he was a hack, but it's fine. Okay, let's talk about Ernest Rutherford. He was working in 1912, so now 15 years after the public discovery of the electron. Ernest Rutherford is doing something called a gold foil experiment, where basically he had, aluminum foil. You can actually make foil out of any metal. So like older people might call it tin foil because before aluminum became cheap, we used to make it out of the metal tin, but now we make it out of aluminum, but you can make it out of any metal. And so he had, I guess he was a baller. He had gold foil. And what he was doing was he took a little radiation source, because this was early enough on that we didn't realize radiation gives you cancer yet. So he took a radiation source and he was just shooting radiation at that gold foil. And they knew enough about radiation at that point to know that there were basically tiny, tiny little particles in the radiation getting shot at the gold foil. And they knew that those particles were very small and should be smaller than the atoms in the gold foil. So he was expecting that because the particles of radiation, it's called alpha particles. These alpha particles are so small, they should be able to just pass straight through those gold atoms. And a lot of them did. A lot of them passed like straight through, but some of them actually deflected at angles and went sideways, which meant they were hitting something. And he was like, there shouldn't be anything for them to hit. And then he did some more experiments on that, trying to figure out what they were bouncing off of. And that's how he discovered the nucleus, a small positively charged region of the atom. Basically the radiation particles were heading toward the gold foil, and he was mostly right that they were very small. The gold atoms, like the size difference was way off. So most of the alpha particles did just pass like straight through between atoms of gold, but some of them hit the nucleus and bounced off and went in other directions. So he was able to figure out that the nucleus must be there. It's surrounded by the electrons. Atoms are mostly empty space though, because most of them could pass straight through the gold atoms. That means mostly there's empty space. Only a few of them were deflecting, which means only a few of them were hitting the nucleus, which means the nucleus must be very small, because if it were bigger, more of the radiation particles would have bounced off of it. He posited that the nucleus contains protons. Later, we discovered neutrons. Neutrons were actually not part of Rutherford's discovery, but I want you to know the nucleus has protons and neutrons, and that all the mass of an atom is in the nucleus. Like technically electrons have mass, but they're so much smaller that they don't contribute to the total mass of an atom, right? Like if you weighed yourself and then you like pulled out one hair and then weighed yourself again, the scale would give you the same number before and after, right? Because that one hair doesn't contribute enough to your total mass that the scale you step on in your bathroom can tell the difference. It's the same idea. Like technically the electrons put more mass on the atom, but they're just so small that it's not worth, like it's not really measurable enough to make a difference. So we say that all mass of an atom is in the nucleus, and that's technically a lie, but functionally true. So then Rutherford had his model of the atom, which was basically there's a positively charged nucleus in the center, and electrons just sort of hang out around the outside. Like yeah, they're just like chilling out there, just floating around randomly. Goodbye, plum pudding model. Yeah. One more time for plum pudding, and now goodbye for real. Okay, let's talk about Niels Bohr. Only 1 year later, in 1913, Niels Bohr, he was a Danish physicist. He basically did a bunch of math. He did differential equations, which is like the next math after you finish calculus. So like really intense level of math. And he discovered that electrons existed in specific orbits. They have a fixed energy in energy levels. And he was able to develop what's called the Bohr model, studying something called the hydrogen emission spectrum, which basically was saying that he looked at a hydrogen atom and he was able to see that as he basically, as a hydrogen atom gains energy or loses energy, it can sometimes push out, like absorb a certain amount of energy, release a certain amount of energy. And he could look at the wavelength of light from the released energy, and it corresponds to different colors. This is actually all stuff we'll talk about in the back half of Unit 4. I wouldn't worry like too much about this right now, but like it's a thing. This is what the hydrogen emission spectrum looks like. And by studying that and doing a bunch of like insane math, he was able to come up with his theory and his model. So we've got the Bohr model, which is also called the planetary model. This is one you're probably familiar with from middle school, because this is the one where it looks like the nucleus is being orbited by electrons, similarly to how planets orbit around the sun. Same basic idea. So we call that the planetary model because it looks like planets around the sun, basically. The planetary model is limited. That's not what atoms actually look like. Atoms actually look closer to something like this, which again, this is a Unit 4 thing. Don't worry about it too much right now. We'll talk about it more in Unit 4. But I bring it up because the reason we use the Bohr model in like middle school and even the first part of high school science and chemistry is because it's easier to understand, like by looking at it. But that's not what atoms actually look like. Like this Bohr model is saying that atoms have a flat rotation of electrons around the nucleus, but atoms are not flat. They are in 3D. Like this, whatever's happening right here, they are in 3D. And the Bohr model is just convenient because, for one, it's like way easier to draw than like this madness. With all these like bubbles in here. Those are called orbitals. Again, we'll talk about them in Unit 4. Don't freak out yet. First of all, the Bohr model is easier to draw. Second of all, it's easier for like a 7th grader to understand, right? If you had shown this to a 7th grader, the 7th grader would like freak out, probably for most kids. So we use the Bohr model for now. For Unit 2, we'll use it for the very first part of Unit 3. We might use it a tiny bit, or for Unit 4. But like eventually we're going to go away from this flat idea and we're going to talk about atoms in 3D. But for now, because I'm going to make you draw atoms several times in this unit, I'm only going to ask you to draw them the easy way. I'm never going to ask you to draw this because I'm not a sadist. But, you know, I want you to be aware atoms are not actually flat like the Bohr planetary model. They are in 3D. There's a timeline here at the bottom of the page. You can note, just for funsies, that Democritus is on there. He had the first theory of atoms in 460 BCE. You don't have to know his name or anything. I just think it's interesting. Dalton basically sort of half rediscovered those ideas of Democritus and brought them back in 1803. And then Thomson in 1897, Rutherford in 1912, Bohr in 1913, 1 year later. And then the really crazy stuff happened in the 1930s, which is ultimately where we ended up getting this model that looks scary, but it's not that scary. Don't worry about it. You're going to be fine. Yeah. So I do want to say that, like, for what it's worth, the neutron wasn't discovered until 1934, which was like way later. Like, look how closely together electrons and protons were discovered. But the thing about neutrons is they're harder to observe because what we observed, what helped us find protons and electrons was their charge. And since neutrons have no charge, it was a lot harder to like find them interacting with stuff. And so it took us another like 20 years on top of it for someone named James Chadwick, I think, to discover the neutron. So, you know, fun fact. But yeah, that's some white men.